Imagine for a second, you're just cruising down the highway.
Right. Clear day, open road.
Exactly. You're behind the wheel of a modern electric vehicle, and you come up behind this slow-moving transport truck.
We've all been there.
Right. So you check your blind spot, pull out into the passing lane, and you press the accelerator to the floor.
Expecting that instant torque.
Yeah, that smooth EV torque, like an invisible hand just pushing you back into your seat. But right at that critical moment, the power completely drops out from under you.
Oh, wow.
Yeah, a little illuminated turtle icon lights up on your dashboard.
The dreaded turtle.
The dreaded turtle. And the car suddenly feels like it dropped an anchor. I mean, it's just limping forward, and you have to carefully guide this incredibly heavy machine to the shoulder of the highway.
Which is terrifying.
Super terrifying. Your heart is pounding, and you're sitting there wondering, what on earth just happened inside that battery pack to cause a failure like that?
It's a completely terrifying scenario, and it's exactly the phenomenon we're unpacking in today's deep dive.
Yes, and we have some really incredible source material to go through today. We're looking at a highly specific, extremely dynamic electrochemical failure.
Right. Known in the automotive engineering world as the P0B24 fault.
P0B24, catchy name.
Right. But this isn't, a situation where you just forgot to plug the car in and the battery slowly died.
Right, this is different.
It's totally different. This is an active aggressive event. We call it cell voltage instability or dynamic internal resistance distortion.
Okay, that sounds intense.
It is. We are talking about a single battery cell out of hundreds in the pack, experiencing severe non-physical voltage fluctuations.
Like spikes and drops.
Exactly. High-frequency spikes, wildly irregular drops, but, and this is the kicker, only under dynamic load.
So it's basically a moving target.
Pretty much, yeah.
Like if the car's just sitting parked in your driveway, the computers might look at the battery and think, oh, everything is perfectly fine.
Yep, 100% normal.
But the ghost only appears when you actually ask the battery to do hard work, like passing that truck.
Precisely. That's when it acts up.
So our mission today for this deep dive is to trace this entire mystery. We're going to start from the microscopic physical flaws that trigger the tantrum, right?
Yeah, the literal root causes.
And then we have to figure out how a car moving at 70 miles per hour actually plays detective to catch this invisible fault, before the battery catches fire.
The diagnostic architecture.
Exactly. Then we'll explore the physical armor engineers designed to stop it, peek inside these obsessive hospital-grade factories where they're built.
The manufacturing side is wild.
It really is. And finally, we'll look at the brutal torture tests these vehicles undergo before you ever even get the keys.
It's a huge journey.
It is. So let's start right at the microscopic origin point. The source material outlines 4 distinct root causes for this P0B24 code, and the first one is mechanical fatigue.
Right, what they call the loose tooth effect.
A loose tooth, like in your mouth.
Sort of, yeah. But this loose tooth actually originates long before the car hits the road. It starts on the factory floor with the welding.
The laser welding, right?
Laser or ultrasonic, yeah. Inside a battery module, you have individual cells, and each cell has these thin metal tabs.
Okay.
You can think of these tabs as the electrical exit doors. They have to be permanently joined to a much thicker metal bridge called a busbar.
Which is like the highway carrying all the power to the motor.
Exactly. It's carrying the combined power of all the cells. But if there is even a microscopic energy drift in the laser during manufacturing.
It's like a tiny drop in power.
Yeah, just a fraction of a watt of power loss.
Right.
Or, if the focal depth of the weld is off by literally a few micrometers.
Wow, that's small.
That's small. If that happens, the metals don't fuse perfectly. You end up with these latent defects.
What kind of defects?
Usually tiny trapped gas bubbles called pores or microscopic cold welds where the metals are touching, but they aren't actually chemically bonded.
Okay, so the car leaves the factory with this completely invisible flaw, and initially it probably drives perfectly, right?
Yep, the metals are touching, so electricity flows just fine.
But then physics takes over. I mean, every single time you charge that battery, the internal chemistry generates heat.
And heat means expansion.
Right. The metal tabs and the bus bar heat up and expand, and then when you park the car, they cool down and shrink.
It's the coefficient of thermal expansion, or CTE. And here's the really insidious part.
Okay, what is it?
The thin tab and the thick bus bar, they often have different thermal mass.
Meaning they heat up at different speeds.
Exactly. They expand and contract at slightly different rates.
Yeah.
So this creates this microscopic shear stress, just dragging back and forth across that imperfect weld joint every single day.
Oh, I see.
And then layer on top of that the constant high-frequency mechanical vibration of simply driving the car.
Right, the road isn't perfectly smooth.
Not at all. Every pothole, every speed bump, every rough patch of asphalt sends shockwaves through the chassis and directly into that joint.
So over thousands of miles, those tiny trapped gas pores from the factory act as stress concentrators.
Yep, they slowly propagate into microscopic fatigue cracks.
Okay, I have a perfect analogy for this. It's like a frayed phone charger cable.
Oh, that's a great way to put it.
Right. You know how you have to bend a dying cable at the exact perfect angle to get your phone to actually charge? And if you bump the table, the connection instantly drops?
Exactly the same principle.
The crack in this battery weld is dynamic. When you hit a bump on the highway, the vibration violently yanks that microscopic fatigue crack open for a fraction of a second.
And when that crack momentarily pulls apart, the physical cross-sectional area where the electricity can flow just plummets.
Because there's literally less metal touching.
Exactly. You're forcing a massive river of current through a tiny microscopic bottleneck. And this brings us straight back to high school physics. Ohm's law.
Right. Voltage equals current multiplied by resistance. V equals I times R.
You got it. When you step on the accelerator to pass the truck, you demand a massive amount of current. That's the I. You need it to flow through that joint.
But if the crack opens, the resistance spikes.
The local contact resistance, the R, spikes instantaneously. Therefore, the voltage drop across that gap must also spike proportionally.
Okay, so that's what they call an I times R transient polarization drop.
Exactly. The car's monitoring sensors suddenly see the voltage of that single cell absolutely plummets.
Even though the cell itself has plenty of energy.
The cell is fine,
Hmm.
but the electrical gateway is momentarily choked off, causing this massive local voltage collapse.
Okay, so that covers the mechanical break. But the second root cause takes us deep inside the actual chemistry of the cell. The source material mentions micro short circuits and punctured separators.
This one is fascinating.
A short circuit sounds like an instant death sentence for a battery, honestly, not a momentary glitch.
Well, a macroscopic short circuit is a death sentence. All the energy dumps at once, and you get thermal runaway and fire.
Right, which we definitely don't want.
But a microshort behaves entirely differently. To understand why, we really have to look at the separator.
What exactly is the separator doing in there?
It's this incredibly thin, highly engineered polymer membrane. It sits physically between the anode,
A negative side.
right, and the cathode, which is the positive side. Its singular job is to prevent the positive and negative active materials from ever touching.
But it still has to let power through, right?
Sort of. It has to be porous enough to let microscopic lithium ions swim back and forth through the liquid electrolyte.
Okay, so it's basically a microscopic chain link fence. It lets the small lithium ions pass through, but keeps the big, dangerous chemical components separated.
The perfect analogy.
So what is actually breaking through that fence to cause the short?
There are two main culprits here. First is conductive dust, or microscopic metal shavings,
Dust. From where?
from the factory. During the winding and stacking of these massive sheets of anode and cathode, if a micrometer-sized flake of copper or aluminum dust settles onto the separator,
Oh no, it gets rolled right up in there.
it gets rolled tightly into the cell. And as the cell organically swells and breathes during normal charging and discharging cycles over its life, the immense internal pressure physically drives that tiny metal flake through the polymer membrane.
Like a slow motion needle?
Exactly like a needle.
So it's basically a ticking time bomb from the factory.
Yeah, unfortunately.
But the second culprit is something the battery actually grows itself, right? Lithium dendrites. The sources say these happen mainly during cold weather fast charging.
Yeah, cold weather is really tough on batteries.
So if the battery is freezing cold, the chemical reaction slows down, right? The lithium ions are trying to swim across the separator and absorb into the anode, but because it's cold, they get sluggish.
It's exactly like a traffic jam at a highway exit.
Right. So what happens to the traffic jam?
We call it intercalation failure. The anode's molecular structure physically cannot absorb the lithium ions fast enough at low temperatures.
So they just pile up outside the exit.
Exactly. Instead of safely embedding into the carbon structure of the anode, the lithium ions start piling up on the surface. They undergo a phase change, actually plating out as solid metallic lithium.
Solid metal, that doesn't sound good.
It's not. Over repeated cold charging sessions, this metallic plating grows outward, forming these sharp, microscopic stalactites,
The dendrites.
the dendrites, and they slowly pierce their way through the polymer separator, until they finally make contact with the cathode on the other side.
Okay, but this is the part that completely melted my brain when I was reading the source notes.
Oh, the self-healing part.
Yes. If a metal shaving or a lithium dendrite punctures the separator and touches both sides, it completes the circuit. It's a short. Why doesn't the battery just catch fire right then and there? The notes describe it as a self-healing phenomenon.
It really comes down to the sheer volume of energy versus the microscopic size of the bridge.
Okay, walk me through that.
When that dendrite finally touches the cathode, it creates a tiny leakage channel. Now put yourself back on the highway, flooring the accelerator.
Right, passing the truck.
You are demanding hundreds of amps of current. Electricity always takes the path of least resistance, right?
Sure.
So suddenly, a large surge of that dynamic load tries to force its way through this microscopic metallic bridge.
But the bridge is tiny.
Exactly. The electrical resistance of that tiny dendrite generates instantaneous, extreme, localized heat. It acts exactly like a microscopic fuse.
Wait, so the heat vaporizes the dendrite.
Literally.
It blasts the metal bridge into gas.
It completely incinerates the microshort. The short momentarily connects, which yanks the cell's voltage down violently, but within milliseconds, the current vaporizes the bridge.
Wow.
It heals the short, and the cell voltage violently rebounds to normal. The battery is internally cauterizing its own wounds.
That is insane. It's basically having a microscopic heart attack and reviving itself over and over.
Pretty much. But to the vehicle's computer, this looks like a terrifying, inexplicable voltage collapse followed by an instant recovery.
Right, the computer doesn't know it healed itself. It just sees chaos. So that's two physical causes, the mechanical weld and the microshort. The third one is described as internal collapse, or electrochemical polarization distortion.
This one is more about the architecture of the cell.
Right. It sounds like the actual chemical engine of the battery is just crumbling.
It is a structural failure, yeah. The active chemical materials, the compounds that actually store the lithium, they're coated onto extremely thin metal foils called current collectors.
What kind of metal?
Usually copper for the anode and aluminum for the cathode. These layers are bound together by chemical adhesives.
Okay.
But through severe aging or continuous deep discharging thermal stress, or even initial manufacturing defects, patches of this active material can physically delaminate.
Meaning they just flake off.
Yeah, they flake off the current collector.
But if chunks of the material are falling off, wouldn't the cell just lose overall capacity? Why does it trigger this violent dynamic fault when you step on the gas?
Because of localized overworking. Think about it. If 20% of your active material has detached, the remaining 80% has to work significantly harder to deliver the same amount of requested power.
Oh, I see.
So when you demand a sudden heavy discharge, like slamming the pedal to pass that truck, you're asking the cell to produce a massive amount of chemical energy instantly.
And the remaining 80% just panics.
The diminished active material physically can't keep up with the chemical reaction rate required. This causes the cell's internal electrochemical resistance to abnormally spike.
The notes actually have a fantastic description of this. It's like the battery has asthma.
That's a great visual.
You step on the gas, asking it to sprint, and it instantly runs out of breath.
Yeah.
The internal resistance skyrockets and the voltage completely collapses.
What then?
Right. But the second you take your foot off the pedal and stop asking for power, the battery catches its breath, the chemical reaction stabilizes, and the voltage floats right back up to looking completely normal.
Exactly. It's a failure of dynamic delivery. The total energy capacity might technically still be inside the cell somewhere, but the physical pathways to deliver that energy rapidly, they've been compromised.
All right, so let's look at the fourth cause. We have broken welds, vaporizing metal needles, and crumbling chemistry.
Right.
But what if the battery itself is in absolutely perfect physical condition? What if the sensors monitoring the battery are just getting lied to?
The ghost in the machine.
The notes call it exactly that, driven by high-frequency electromagnetic interference, or EMI.
This is the scenario that drives software engineers completely mad.
I bet. The battery is flawless, but the car thinks it's dying.
Right, because the diagnostic system is being blinded by electromagnetic noise. Modern electric drivetrains rely on an inverter to convert the direct current from the battery into the alternating current that actually spins the electric motor.
So DC to AC.
Right. And to do this efficiently, the inverter uses these high-power semiconductor switches, specifically silicon carbide or IGBTs.
And these things are switching massive amounts of voltage on and off, like tens of thousands of times every single second to create that AC waveform, right?
The switching frequency is incredibly aggressive. And every time one of those high voltage switches snaps open or closed in microseconds, it creates a massive electromagnetic pulse.
Like a shockwave.
Yeah, it generates intense common mode EMI noise. The motor inverter is effectively acting like a high-power radio jammer, just broadcasting invisible radio frequency static all around the powertrain.
And the tiny, super sensitive wires that run from the battery cells to the computer chips are just sitting there in the middle of this static.
Exactly.
If those sampling wires aren't perfectly shielded, they act like literal antennas. They pick up that high-frequency switching noise.
And the analog-to-digital converter, the chip whose only job is to read the cell voltage, gets totally overwhelmed.
So it reads the electromagnetic static as actual massive voltage spikes and drops.
Yep. It sees a phantom voltage collapse that never actually happened chemically inside the cell. It's a pure hallucination caused by the motor spinning up.
Okay, so we have a mechanical crack, a short-circuiting dendrite, crumbling chemistry, and a hallucinating sensor. And here is the core problem, as I see it.
What's that?
To the main computer, every single one of these looks utterly identical.
They do. They really do.
They all manifest as a sudden, impossible voltage drop the second you step on the pedal. So how on earth does a car moving at highway speeds figure out if it's dealing with a hallucination or a battery that is actively tearing itself apart?
This is where things get really cool. It requires an incredibly sophisticated technical architecture, bridging the physical edge sensors and complex software algorithms.
And then detective work, basically.
Right. It's a process of soft-hard code diagnosis. And it starts at the very edge of the data pipeline with the analog front end, or the AFE chip.
The AFE chip. Okay, so it's not just a simple digital voltmeter sitting on the battery, is it? The source highlights high-frequency differential sampling and a self-calibrating offset circuit. Break down how this actually captures the data.
Sure. So the AFE is an automotive-grade silicon chip, and it's mounted directly on the local control boards inside the battery pack.
So it's right in the trenches.
Exactly. It has to measure the analog voltage of individual cells and convert that into digital data the main processor can actually understand. But it does this using differential sampling.
What does that mean in practice?
Instead of just measuring a cell's voltage against a generic ground wire, it uses two dedicated wires to measure the precise voltage difference purely across the positive and negative terminals of that specific cell.
Okay, so it's isolating it.
Right. This inherently rejects some of that localized noise we talked about.
And what about the self-calibrating offset? That sounded really intense.
Well, silicon chips actually change their electrical behavior slightly based on their own temperature.
Really? Just from getting warm?
Yeah. Inside a hot battery pack, a chip might start reading 5 millivolts higher just because it's physically warm, which totally ruins the data precision.
Oh, that's a problem.
So the offset circuit forces the chip to constantly disconnect from the battery, measure its own internal baseline zero, adjust its math, and then reconnect to the battery.
Wait, it unplugs itself to check its own math?
Yes. It does this continuously, guaranteeing that the voltage data is completely immune to temperature drift. And it samples this data at the millisecond level.
So the AFE is taking thousands of flawlessly calibrated high-definition snapshots of the voltage every second.
Exactly.
But we know that data is still potentially infected with that high-frequency EMI noise from the motor, right?
Oh, definitely.
So before the main software brain even sees those numbers, it hits a physical roadblock. The notes describe a second-order RC low-pass digital filter. How do a resistor and a capacitor physically scrub this data clean?
It is brilliant physical filtering. An RC filter is a circuit made of a resistor and a capacitor.
Okay.
Imagine water flowing through a pipe. The electrical current carrying the voltage signal is the water. The resistor is a physical narrowing of that pipe. It limits how fast the water can flow.
Got it. And the capacitor?
The capacitor acts like a surge tank connected to the pipe right after that restriction.
Okay, so if a real slow chemical voltage drop happens, like the battery just naturally draining, the water level slowly drops, the surge tank drains with it, and the true signal passes through to the chip.
Exactly. But if a massive, high-frequency EMI voltage spike hits the wire...
A sudden, violent surge of water.
Right. The resistor slows down the initial punch, and that excess energy immediately dumps into the capacitor surge tank. The capacitor literally swallows the high-frequency spike before it can ever reach the AFE chip.
That is so clever.
And by chaining two of these together, a second-order filter, they create this steep physical cliff that essentially blocks the high-frequency static from the motor while letting the slower, meaningful battery voltage trends glide right through.
So the hardware scrubs the data, and now it enters the software detective layer, the battery management system, or the BMS.
The brains of the operation.
The source discusses the algorithm constantly calculating the DVDT, the dynamic slope, and comparing reality against an equivalent circuit model, the ECM.
Right, the equivalent circuit model is really the foundation of modern battery diagnostics. It is a mathematical digital twin of a perfect, healthy battery running in real time inside the computer.
A digital twin, I love that.
Yeah, so the BMS looks at how much current you, the driver, are demanding, feeds that number into the digital twin, and calculates precisely how a healthy cell's voltage should respond.
And a healthy electrochemical discharge is just a smooth, predictable curve, right?
Always.
So it's doing calculus in real time. The DVDT isn't just looking at the absolute voltage, it's looking at the rate of change, the speed of the drop.
Exactly.
If a healthy battery smoothly curves down, but a broken weld or a vaporizing dendrite drops off an absolute cliff in 2 milliseconds.
The algorithm compares the real-time DVDT against the digital twin and immediately flags a massive mathematical discrepancy.
The math doesn't add up.
The software deduces that a chemical battery simply cannot drop its voltage that fast naturally. The laws of thermodynamics just don't allow it. Therefore, this is not a dead battery. This is a catastrophic hardware failure.
Okay, hold on, though. Let me play devil's advocate.
Go for it.
If I hit a massive pothole doing 70 miles an hour, the vibration violently shakes that weld, right? The crack opens for a tenth of a second, the voltage drops off a cliff, and the DVDT spikes. Does the algorithm instantly panic, declare a catastrophic failure, and shut off my car in the passing lane?
Well, if it relied on a single data point, it absolutely would.
And that would be incredibly dangerous.
Very dangerous, which is exactly why the system utilizes strict debounce thresholds. The software requires a sustained confirmation before taking any drastic action. It's a multi-layered logic gate.
What are the exact conditions the software has to verify to be sure it's a real failure?
First, the magnitude of the dynamic voltage drop must cross an extreme threshold. The source provides a benchmark here. The delta V, the sudden drop, must be greater than or equal to 400 millivolts.
Okay.
And crucially, this must occur while the system is pulling a dynamic load of greater than or equal to 100 amps.
So it requires heavy current and a massive drop simultaneously.
Massive anomaly under heavy load. That starts the clock.
It initiates the debounce timer.
Exactly. The anomaly must persist beyond a specific time threshold, typically calibrated somewhere between 500 milliseconds and 2.0 seconds.
2 full seconds. In a computer doing millions of calculations a second, 2 seconds is an absolute eternity to wait while a battery is throwing a fault.
It is an eternity. But it is intentionally calibrated that way specifically to filter out your pothole scenario.
Okay, walk me through the pothole scenario then.
You hit the bump, the crack opens, the voltage collapses, the software flags the massive DVDT anomaly and starts the 500 millisecond stopwatch.
Right.
But a fraction of a second later, the car's suspension settles, the mechanical vibration stops, the metal weld physically touches again, and the voltage instantly recovers.
Oh, so the computer sees the recovery before the timer runs out.
Yes. The computer sees the recovery before the 500 millisecond timer expires, so the system immediately wipes the timer and resets. It categorizes the event as a momentary mechanical blip, saving the driver from a terrifying highway shutdown.
But if the voltage stays completely collapsed for that entire debounce window, the computer knows the weld isn't just vibrating, it's structurally broken. The short isn't healing.
Exactly. That's when it triggers the confirmed diagnostic trouble code, the DTC.
The computer is now certain the car is in danger. So what is the physical fail-safe response? How does the car actually protect itself and the driver?
It initiates a violent... So if you lift your foot off the pedal, regenerative braking slams a huge wave of inward current back into the battery. Forcing high current into a high-resistance cell causes its localized voltage to instantly and violently skyrocket.
Like pushing water back through a tiny hose.
Exactly. It would hit the critical OVP limit in milliseconds.
And what happens if it hits OVP?
The battery protection system physically blows the main explosive contactors open.
Explosive contactor.
Yeah, it entirely severs the high-voltage battery from the rest of the car to prevent a fire. You instantly lose all propulsion, power steering, and power brakes at highway speeds.
That's a total blackout.
So by disabling regen, the very millisecond the fault is confirmed, the BMS sacrifices efficiency to prevent a catastrophic total vehicle blackout.
That is incredibly smart defensive logic. It kills the regen to stop a voltage spike. But what does it do about the power actually going to the wheels?
That triggers the discharge and gear reading protocol. The BMS instantly slashes the maximum allowable discharge power to the motor, typically by a massive 60%.
60%.
This is the exact moment you, the driver, feel the car drag an anchor. The dashboard lights up with the malfunction indicator lamp, the MIL, and the turtle icon appears.
The turtle has arrived.
The car is intentionally choking its own performance so that the motor can't pull enough current to drag the broken cell's voltage down into an undervoltage protection, or UVP, critical state.
But what if the cell is just completely giving up? What if 60% power is still too much, and the voltage is still plummeting toward the absolute floor?
If the voltage sag approaches the UVP limit, despite the severe derating, the car escalates to the final safety protocol, limp home mode.
Limp home mode.
It entirely disables normal EV driving. The vehicle enters a heavily restricted low-voltage crawling state. It provides just enough momentum, perhaps 10 or 15 miles per hour, to allow the driver to physically navigate to the shoulder of the highway.
So the entire architecture is designed to manage a controlled, predictable shutdown, rather than allowing a sudden, violent loss of control. That's amazing. I mean, from a 10-micrometer mechanical crack to the AFE chip catching the voltage cliff, to the RC hardware filtering the noise, the digital twin confirming the math, the 2-second debounce timer verifying it's not a pothole, to the 60% power cut that saves the car from a blackout.
It's a lot.
The timeline of this entire diagnostic cascade is measured in milliseconds.
It is a phenomenal achievement in systems engineering, truly. But as any engineer will tell you, detecting a catastrophic fault and limping to the shoulder is still a failure mitigation.
Right.
The holy grail of engineering is preventing the fault from ever existing in the first place.
And that brings us to the design phase. Section 3 of the source material. How do you design a battery that fundamentally refuses to fail? The sources break down the DFMEA preventative measures.
Right, DFMEA, design failure mode and effects analysis.
So this is how engineers quantify risk before a single part is manufactured, right?
Exactly. And in this DFMEA matrix, the PAB24 fault is assigned an extremely high severity score of 8.
An 8 out of 10.
Yes. This classification means the failure poses a major risk of sudden, unexpected power loss while driving, potentially occurring without sufficient warning to allow the driver to safely maneuver.
Okay, so it's a huge deal.
Because a severity 8 is unacceptable, the mechanical and electrical countermeasures must be incredibly robust. Let's look at how they address the mechanical stress first.
Well, the root cause was thermal expansion and road vibrations slowly tearing the rigid laser welds apart. The notes refer to the solution as mechanical origami and stress relief geometry.
Mechanical origami, yeah.
You can't stop the metal from getting hot and expanding, obviously, so how do you stop it from breaking the weld?
You build flexibility into the rigid structure. Instead of using stiff, solid wires to connect the sampling chips to the battery cells, engineers utilize FPC, flexible printed circuits.
Flexible circuit.
These are thin, highly durable ribbons of circuitry. But it's not just the material, it's the geometry. They design these circuits with specific undulating shapes, usually an S-shape or a wave-shaped bend right before the weld point.
Oh, I instantly pictured this like the expansion joints on a massive bridge, or the flexible foundation joints in earthquake-proof skyscrapers.
That's a great comparison.
Right. When the concrete gets hot in the summer, it expands. If the bridge was totally rigid, it would buckle and shatter. But with a zigzag joint, the bridge just harmlessly compresses the zigzag.
The principle is identical. It's called strain relief. When the battery cell heats up, it expands, or when the vehicle chassis shakes violently on a corrugated dirt road, that S-curve acts as a microsuspension spring.
I love that. A microsuspension.
The flexible ribbon physically bends and absorbs the shear stress. Consequently, the actual microscopic weld point where the circuit meets the bus bar experiences effectively zero pulling force.
So the geometry isolates the rigid weld from the dynamic movement of the vehicle, stopping fatigue cracks from ever initiating.
Geometry defeating material science. It's beautiful.
It really is. Okay, so that handles the mechanical loose tooth. But what about the micro shorts? The lithium dendrites and the metal shavings slowly pushing their way through that polymer separator. How do you stop a microscopic spear?
You reinforce the polymer with microscopic ceramic armor.
Ceramic armor.
Engineers upgrade the standard separator film to something much more advanced. It's a separator inherently coated with a dense layer of high-strength ceramic aluminum oxide, or Al2O3.
Aluminum oxide ceramic. Isn't that the same material class used in, like, ballistic body armor and tank plating?
It is, just scaled down to the micrometer level inside the cell.
Why is this specific ceramic so effective against a tiny metal needle?
Two critical reasons. First is purely mechanical hardness. The ceramic lattice is physically denser and harder than the metallic lithium dendrite or a stray copper shaving.
So it's literally a shield.
When the dendrite tries to grow through the separator, it simply hits a microscopic brick wall and cannot penetrate. It drastically increases the mechanical puncture resistance of the cell.
Okay, that makes sense. And the second reason?
Thermal stability. If a microscopic flaw somehow does create a tiny localized short, we know it generates intense heat.
Right, the vaporization we talked about.
Well, a standard plastic polymer separator will melt and shrink away from that heat source. When it shrinks, the tiny short becomes a massive hole, leading to a catastrophic thermal runaway fire.
Oh, so the plastic makes it worse.
Exactly. The ceramic layer, however, has an astronomically higher melting point. It refuses to melt, shrink, or deform at those temperatures.
So it holds the line.
It physically holds the barrier completely intact, localizing the heat and preventing a cascading short circuit. It provides intrinsic material-level safety.
Wow. So we have S-shaped suspension springs to stop the vibrations and ceramic ballistic armor to stop the shorts. That leaves the final root cause, the EMI ghost noise from the motor inverter. How do we design electronic earplugs?
We implement what is known as a high-immunity front-end signal chain.
A layered defense.
Exactly. We already discussed the physical hardware door, the second-order RC low-pass filter on the circuit board that swallows the massive spikes.
Right, the water surge tank.
But hardware filters aren't perfect. Some high-frequency jitter will still leak through that door.
So what sits behind the door to catch the leaks?
The software security guards. The raw digital data passed from the AFE chip is immediately run through software-based digital signal processing.
Okay, DSP.
The code utilizes complex mathematical bandpass and low-pass filtering algorithms. It calculates moving averages and mathematically smooths out the incoming data array.
So the hardware takes the brute force punch of the EMI, and the software mathematically erases the remaining high-frequency static.
Working in perfect tandem, they guaranteed the BMS only reacts to true, clean electrochemical data.
It's just an incredibly resilient design, but having a flawless design on a computer screen brings us to a massive, unavoidable reality check.
The manufacturing floor.
Exactly. And brilliant design is completely useless if the factory building it is sloppy. And these factories are churning out millions of these individual battery cells every single month. How do they guarantee this microscopic perfection at an industrial scale?
This takes us from DFMEA into PFMEA, process failure mode and effects analysis. The mandate on the factory floor is zero manufacturing escapes.
Zero escapes, that's a high bar.
They achieve this through layers of relentless, real-time process control. Let's look at the laser welding process first, which we know is the origin of those micro cracks. They implement key control characteristics, or KCC, monitoring on every single weld.
So the lasers aren't just firing blindly. What exactly is the system watching while it welds?
It is an entirely closed-loop statistical process control, or SPC, system. The monitoring hardware tracks every single microscopic pulse of the laser in real time.
Every single pulse?
Yes. It measures the absolute spot position of the beam, the peak power delivery down to the fraction of a watt, the exact flow rate of the protective shielding gas preventing oxidation, and the micrometer per second travel speed of the laser head.
Okay, so if the laser's power dips for literally 1 millisecond, potentially creating a poor or a cold weld like we discussed earlier,
the SPC system detects the parameter deviation instantly, aborts the sequence, flags that specific battery module as defective, and automatically routes it off the line to the scrap heap.
just immediately scrapped.
Immediately.
That covers the machine's parameters, but how do you verify the actual liquid metal? I mean, how do you know the molten pool of copper and aluminum actually mixed perfectly? You can't crack the weld open to look inside.
No, you can't. So you deploy inline 3D X-ray vision.
X-ray vision.
The battery industry has actually adopted an incredible technology originally developed for medicine. It's called OCT, optical coherence tomography.
Wait, I know OCT. Eye doctors use it to map the microscopic layers of the human retina. They use retinal scanners on car batteries.
It is the exact same interferometry principle, yes. OCT splits a beam of light, bouncing one half off a reference mirror and the other half deep into the subject. By analyzing the interference pattern of the returning light waves, it builds a micrometer resolution, 3D topographic map of the subsurface structure.
That is mind-blowing.
In the battery factory, this OCT scanner is mounted directly adjacent to the laser head. As the laser is violently melting the metal, the OCT is looking straight into the molten pool. performing 100% real-time, non-destructive penetration depth monitoring.
Wow.
It verifies that the weld physically penetrated deeply enough into the bus bar, and it can actively see if there are any microscopic gas bubbles trapped inside the solidifying metal.
So it's performing a 3D medical ultrasound on every single weld as it happens.
Pretty much.
The source notes also mention a vacuum system paired with this laser. What is that for?
Well, welding liquid metal inherently creates spatter, microscopic droplets of boiling metal flying into the air, which we call weld slag.
Oh, right.
If a single droplet of that slag lands inside the battery enclosure, it becomes the exact metallic shaving we discussed earlier that eventually punctures the ceramic separator.
Right, the metal dust-ticking time bomb.
To eliminate this risk, the entire OCT welding head is shrouded by a high-velocity, negative-pressure vacuum nozzle. The instant a microscopic spark of slag is ejected from the weld pool, the vacuum physically sucks it out of the air before it can ever land on the battery.
So that stops the welding sparks. But the clean room section of this document is wild. The third root cause was standard environmental dust and metallic shavings getting rolled into the cells. Just how clean is the room where the raw cells are actually wound together?
The winding and assembly process takes place in the ultimate clean room, specifically an ISO Class 6 or higher ultra-clean environment, operating under constant negative pressure.
Okay, I want to focus on this because it seems counterintuitive to me.
How so?
My house is definitely not ISO Class 6, obviously, but usually clean rooms use positive pressure, right? They pump extra filtered air into the room so that if you open a door, the clean air pushes outward, keeping the dirty factory dust out. Why does the outline specifically emphasize negative pressure for this battery assembly room?
That is a brilliant catch, and it really highlights the dual hazard nature of battery manufacturing. You are absolutely right that positive pressure keeps external dust out. However, the raw active materials being handled in these specific assembly areas, the microscopic cathode powders containing nickel, cobalt, and lithium.
They're dangerous.
They are incredibly hazardous, toxic, and highly conductive. If those microscopic conductive powders escape into the broader factory, they will settle on other electrical components and cause catastrophic short circuits everywhere.
So the room is under negative pressure to trap the highly conductive, dangerous battery dust inside the zone, protecting the rest of the factory.
Precisely. The HVAC system pulls more air out of the room than it pushes in. If a door opens, air rushes in, preventing the toxic conductive cathode dust from escaping.
But wait, if air is rushing in, doesn't that bring the dirty factor dust into the clean room, ruining the battery cell?
It would, which is why the airlock systems and the incoming air filtration are vastly oversized. The air rushing in is heavily scrubbed through HEPA filters before it ever enters the negative pressure zone.
Okay, that makes sense.
Inside the room, workers wear full head-to-toe particulate suits. And most importantly, the room is heavily instrumented with real-time dynamic dust monitoring lasers.
Dust lasers.
If the particulate count in the air spikes by even a fraction in one corner of the room, the alarms trigger, the assembly line immediately halts, and the environmental anomaly is purged. This guarantees zero foreign metal shavings enter the cells.
It really is like they're assembling components for a deep space satellite.
It is that strict.
Okay, so the battery is perfectly built in a spotless room. But before it gets put onto a truck, it has to pass a final exam. The notes call this end-of-line shock therapy, or EOL testing. What happens here?
Every single high-voltage connection in the finished battery pack is tested with a highly calibrated micro-ohm meter. This device measures electrical resistance down to the millionth of an ohm.
1/millionth of an ohm.
The factory standard is absolute. The contact resistance of every busbar weld must measure strictly less than 0.05 milliamps. If a single weld measures 0.06 milliamps, the entire pack is rejected.
Okay, I have to challenge this testing methodology.
Go ahead.
What if the laser had a glitch and the weld has a massive internal crack, but the two pieces of metal are currently sitting perfectly flush against each other?
The hanging by a thread scenario.
Exactly. It's literally hanging on by a microscopic thread of metal. Wouldn't the micro-ohm meter send its tiny measuring current across, read a perfectly acceptable low resistance because the metals are touching, and just pass a completely broken battery?
You have just identified the exact flaw in standard resistance testing, and it is the precise reason the factory utilizes the pulse discharge test to find those hidden defects.
Oh, there's another test.
A simple low-voltage measurement will absolutely be fooled by a weld hanging on by a thread. To find the weak thread, you have to try and burn it.
How do they burn it safely?
Instead of a gentle measuring current, the end-of-line tester blasts the battery pack with a massive high-frequency current pulse. It is the electrical equivalent of an artificial lightning strike.
A lightning strike.
Immediately following the pulse, the battery is sent into a high-temperature aging oven for a prescribed duration.
They're intentionally trying to break the newly built battery.
They are thermally and electrically torturing it to amplify microscopic flaws. If a weld is hanging by a microscopic thread, that massive current pulse forces so much energy through that tiny bottleneck that the thread of metal rapidly superheats and warps.
Oh, and then the oven.
The subsequent high-temperature oven baking causes the dissimilar metals to expand, physically tearing that weakened thread apart. When the pack comes out of the oven, they measure the resistance again.
And the hidden flaw is completely exposed.
Exactly. The resistance will have massively spiked above 0.05 milliamps, and the pack is caught before it ever ships.
So the battery is perfectly designed, and the manufacturing process has proven it is flawlessly built. But we still aren't done.
Not even close.
Before the automaker will ever put this battery into a car and hand the keys to a consumer, they have to prove that the entire integrated system, the physical design, the sensors, the software algorithms, actually works together in the real world.
This is the ultimate crucible, Section 5, DDP&R Mass Production Verification, Design Verification Plan and Report. This is where the engineers subject their own creation to absolute extremes to prove the safety systems function as designed.
The first trial is called shake and bake, or thermal fatigue testing. This is specifically targeting that S-shaped flexible wire we talked about earlier, right? The mechanical origami that is supposed to absorb vibrations.
Correct. They have to prove that the flexible circuit will actually survive a decade of daily driving. So they take fully assembled battery modules and lock them inside a severe environmental testing chamber.
Just a normal testing chamber.
This chamber doesn't just get hot and cold, it induces violent thermal shock. It swings the ambient temperature from negative 40 degrees Celsius, which is Arctic freezing, to 85 degrees Celsius, scalding heat, in under 10 seconds.
In under 10 seconds. The expansion and contraction forces on the metal would be incredibly violent at that speed.
It's designed to induce rapid material fatigue. And while the battery is screaming through these thermal shocks, the entire assembly is strapped down to a 3D vibration table.
At the same time.
At the same time. This table violently shakes the battery in all three axes simultaneously, specifically mathematically tuned to match the ISO 16750 TAF3 automotive standard.
What does that standard actually simulate in the real world?
It replicates the exact harmonic frequencies of the worst real-world driving conditions, hitting deep potholes, rattling over corrugated gravel roads at high speed, and the internal vibrational resonance of the vehicle's own drivetrain.
Wow.
And they subject the battery to this combined thermal and vibrational torture for 300 hours consecutively.
300 hours of freezing, boiling earthquakes. When they finally turn the machine off, how do they know if the S-shaped wire actually did its job?
The pass-fail criteria are strictly microscopic. Engineers physically dismantle the tested modules and place the weld joints under a scanning electron microscope, or SEM.
Okay, looking really close.
They are examining the metallurgical crystalline structure. The engineering standard dictates that there cannot be any fatigue slip bands, which are the microscopic stress lines that eventually become cracks, and absolutely no physical cracks larger than 10 micrometers.
10 micrometers. To give everyone a sense of scale, a standard human hair is about 70 micrometers thick, so they are hunting for stress cracks that are 1/7 the width of a hair after 300 hours of torture.
Exactly. And electrically, the resistance across that tortured joint must still remain strictly under the 0.05 milliamp limit. If the wire cracks or the resistance drifts, the design fails DVP&R and must be entirely re-engineered.
So the mechanical origami survives the earthquake. Next, they have to test the software and the electronic earplugs, the filters designed to block out the motor inverter's EMI noise. The source calls this the noise injection test. How do you rigorously test for invisible ghost signals?
You build a digital ghost. The engineers utilize an HIL simulator, hardware in the loop. They take the actual physical battery management system computer chip and plug it into a massive supercomputer array.
Got it.
The supercomputer simulates the entire electric vehicle. The motor spinning, the driver pressing the pedals, the battery discharging. Then, they actively and aggressively inject extreme electromagnetic noise directly into the physical sensor wires connecting to the BMS.
They are actively trying to jam the car's radar.
It is an electronic warfare attack on their own computer. They inject high-power noise sweeping from 10 kilohertz to 20 kilohertz, forcefully creating massive, violent voltage spikes of plus or minus 1.5 volts overlaid on top of the simulated battery voltage.
So they're just screaming fake signals at the BMS to see if it panics and falsely triggers the P0B24 turtle light.
Exactly.
What does the BMS have to do to pass this electronic attack?
It must mathematically recognize the lie and ignore it. First, the physical hardware RC filter must successfully attenuate or muffle the raw noise power by at least 40 decibels.
Okay, the hardware does its part.
Second, the software algorithm must look at the massive voltage spikes, calculate the dV/dt dynamic slope, and recognize that a voltage change greater than 0.5 volts per 10 milliseconds is thermodynamically impossible for a real chemical battery.
So the software sees the impossible math and says, this isn't real, this is just noise. What does it actually do with the fake data, though? Does it just go blind?
It executes a critical safety protocol called hold last valid value.
Hold last valid value.
The software essentially closes its eyes to the screaming noise and uses the last known, verified good voltage reading to keep the vehicle operating smoothly.
That's smart.
The pass criteria mandate that during this entire barrage of electronic noise, the state of charge estimation, the battery percentage displayed on the dashboard, cannot drift by more than plus or minus 1.5%. And it is absolutely, categorically forbidden for the system to trigger a false P0B24 shutdown.
The driver should never even realize the electronic attack is happening.
Exactly.
It acknowledges the lie, ignores it, and keeps driving. That is brilliant. But this brings up the most crucial scenario. How do they prove the software can actually tell the difference between a real catastrophic physical break that requires a shutdown and just a really bad ghost signal?
That is the final, ultimate software logic test. The IV correlation or current voltage correlation.
Right, because earlier we established that to the computer, a physically broken weld and a blast of EMI noise both initially look like sudden, massive voltage jumps.
Exactly. So on the HIL supercomputer, the engineers run two highly specific simulated scenarios. Scenario A is real danger.
Okay.
They simulate the car driving aggressively on the highway. Right as the simulated driver floors the accelerator, pulling a massive dynamic spike of current, the engineers inject a massive, perfectly synced voltage drop into the sensors.
High current, perfectly synced with a massive voltage drop.
The software algorithm must instantly recognize the correlation. High current perfectly timed with a severe voltage drop unequivocally equals an I times R transient polarization event.
It means the physical weld just snapped open.
The software must immediately start the debounce timer, officially confirm the fault within a strict 15-second diagnostic window, and then act within a 2.0-second FTTI.
FTTI, fault-tolerant time interval?
Right. It means the system has a maximum of exactly 2.0 seconds from the confirmation of the fault to successfully drop the powertrain output by 60%, completely disable regenerative braking, and permanently disable DC fast charging.
And if it doesn't?
If it fails to execute those safety commands in 2 seconds, the test is a failure.
So that's scenario A, real physical danger, and the car successfully neuters itself to protect the driver. What is scenario B?
Scenario B is fake danger. The simulated car is sitting perfectly still in a parking lot. The electric current flowing from the battery is exactly 0 amps.
0 amps. Nothing moving.
But the engineers intentionally inject wild, violent voltage drops into the sensors.
So the voltage is collapsing, but there is absolutely zero power flowing.
The software algorithm must look at the current sensor, verify 0 amps, and execute pure logical deduction. Ohm's law dictates V equals I times R. If the current I is 0, the voltage V mathematically cannot drop due to an internal resistance spike.
Oh, wow.
Therefore, the software must deduce that the battery cell itself is perfectly fine, and this is entirely caused by a broken sensor wire or extreme EMI noise.
So it realizes the sensor is lying. What does it do?
It logs a pending diagnostic code deep in the system memory for a mechanic to investigate later, but crucially, it must not cut propulsion power to the driver, and it must not trigger the turtle light. It flawlessly distinguishes between a hardware safety threat and a sensor anomaly.
Pure mathematical deduction saving you from a false breakdown. That is incredible. Okay, the very last point in the outline is production data verification. They don't just verify the car's computers, they actually have to verify the factory's automated systems.
Oh, yes. The automaker must mathematically prove the factory is capable of perfection. They audit months of live production data from the weld monitoring systems and the end-of-line testing rigs.
Months of data.
They must statistically prove that the end-of-line system successfully intercepted 100% of all battery parts that possessed a resistance greater than or equal to 0.05 milliamps.
And there is a specific statistical metric for this, right? The CP.
Yes, the Process Capability Index, or CPK. The factory must maintain a strict, proven CPK of greater than or equal to 1.67.
What does 1.67 actually translate to in the real world?
In statistical manufacturing terminology, a CPA 1.67 equates to operating at roughly a 5 sigma level of quality control.
5 sigma.
It mathematically dictates that the manufacturing process is so profoundly controlled and the acceptable tolerances are so tightly bound that the statistical probability of the factory producing and shipping a bad weld is less than 1 in a million.
Wow.
It proves that the perfect factory isn't just an engineering theory, it is continuously validated statistical reality.
Let's just zoom all the way out and look at the sheer scale of the journey we've just been on. I mean, we started with a microscopic 10 micrometer mechanical crack in a laser weld, or a single micrometer size speck of copper acting like a needle inside the cell.
The tiniest defects.
Right, and we broke down the exact physics of how those tiny defects create massive, violent voltage collapses the second you step on the accelerator. We watched the car's analog front-end chip and RC filters scrub the noise, and the software algorithm mathematically deduced the truth using real-time calculus and strict debounce logic.
It's quite the chain of events.
It really is. We saw the incredible lengths engineers go to, from designing S-shaped, flexible microsuspensions to coating polymer sheets in ballistic ceramic armor just to prevent the failures from ever forming. And then we watched them lock these batteries in freezing, vibrating torture chambers and blast them with electronic warfare just to prove the whole symphony actually works.
It's exhaustive.
It fundamentally changes how you view a vehicle. It shows you just how much invisible, genius-level engineering is happening underneath your seat, actively calculating physics in real time to protect you every single time you press that pedal.
It is a phenomenal, highly localized defense mechanism. But, as we wrap up this analysis, I actually want to leave you with a broader, forward-looking question.
Yeah.
Something directly pulled from the frontier of this engineering space.
Let's hear it.
Today, we focused entirely and deeply on P0B24. This is a highly localized, highly dynamic resistance drop occurring in a single specific cell.
Right.
It is an acute, sudden, violent anomaly. But consider this. What happens when the entire battery pack slowly, predictably, and inevitably degrades over 10 or 15 years of driving?
Just general aging.
Right. What happens when the overall direct current internal resistance of every single cell collectively rises together?
So a total slow motion system fade instead of a sudden microscopic break.
Exactly. That gradual collective degradation is a completely different fault code, known technically in the industry as P0AC4. It is the slow, inevitable creep of systemic chemical aging.
Interesting.
The provocative question for engineers today is, how do the vehicle's overarching defense mechanisms and software logic differ when fighting a sudden, violent, localized anomaly versus managing a slow, system-wide degradation?
Oh, that is a fascinating distinction. It is the fundamental difference in how the software monitors the acute safety of an EV, like deploying millisecond reactions to catch a microscopic broken weld before it sparks a fire, versus how it monitors the overall health and longevity of the vehicle over a decade.
Yeah.
Safety requires instantaneous mathematical deduction. Health requires the system to slowly analyze years of subtle chemical shifts. That is absolutely something for you to chew on the next time you plug your car into a charger.
Definitely.
Think about the thousands of lines of code working silently in the background, deciding in real time whether your battery is simply getting old or if a single cell is actively tearing itself apart.
It entirely changes the way you look at the dashboard lights.
It really does. So the next time you pull out to pass that slow-moving truck on the highway and you feel that smooth, uninterrupted wave of electric torque pushing you forward, just take a second to remember the mechanical origami, the ceramic armor, the vacuum sealed clean rooms, and the split-second mathematical logic gates that are working furiously in the background to keep that tail light off and keep you moving safely forward. Thank you for joining us on this deep dive.